So far, what we have learned is actually very significant part of machine learning. We learned about Python, we learned about NumPy, we learned about pandas, and we also learned about the linear algebra and the matplot. Afterwards, we learned about the end-to-end project, and we, of course, have gone through the basic definitions of machine learning, like what is classification and things like that. All right, so today we are going to get started with the second chapter, or you can say third chapter of machine learning called classification. We'll understand what is classification and how to solve a very interesting, historically interesting problem of recognizing handwriting. And we'll do that now, and then later during the deep learning time, we will improve its performance. The theory related to the classification will remain same even during the neural networks. And here, what we're going to learn is a very, very interesting and important concept on classification. Today, we are going to get started with classification. So we will be using this one. All right. Okay. So the problem that we did in case of the end-to-end project, the housing prices, specifically the California housing prices, where we were trying to predict the prices, it was basically a regression task. All right, so it was essentially a regression task. And the second good question that we have to answer is how to solve the classification problems. Now, machine learning problems are classified based on three criteria: whether the problem requires human supervision or not, whether it requires learning incrementally or not, and how well the problem or the model generalizes. Okay, so that way the machine learning is classified into these buckets. The ones that are classified based on human supervision, one of the machine learning types is supervised. So we talked about regression last time when we talked about end-to-end project, and now let's learn about classification. Now, classification is basically identifying to which label something belongs to. For example, given an image, we have to predict whether it contains 5 or not 5, right? That's a simplified image, right? That's a simplified problem, whether given an image, whether it is 5 or not 5, all right? And the second one on the right hand side is given an image, we have to predict whether it's 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? Which of the numeral is it given an image? So the one that is on the left is called the binary classification, and the one on the right is multi-class classification. Okay, classification is the task of identifying which category a new observation belongs to. On the basis of observation, whose category is known. All right. So examples of classifications are, um, right? So classifying emails as spam or not spam is another example of classification. All right. It's another example of classification given the, all right, given the emails, if you have to predict whether it's a spam or it's a email, this is an example of classification. Now, the third project that we'll do as part of this chapter is um, for one project we will do with respect to two projects we'll do with respect to the predicting the handwriting recognition. The third one we'll do with respect to cleaning up images. And the fourth one we will do with respect to the iris dataset. What is iris dataset? Iris dataset is basically classifying, it's a dataset of lots of flowers in which we have, it's not really photos that are given to you as opposed to the common misunderstanding initially. So what is given to us is the length of sepal and petal, and we have to predict what what is that species of the iris flowers. The iris flowers are many: Setosa, versicolor, virginica. The three are the kinds of that. And given the length of sepal and petal, we have to predict what kind of what is that species of iris. All right. So that's the one of the projects that we are going to do. Now there are many other examples. One is whether classifying a credit card transaction as fraudulent or genuine. Doing the face recognition, given an image, we need to find out, uh, given an image, we have to find out whether it has faces. Second, given a face, we have to identify whose, whose face is it, okay? We have a database of 100 people and we want to recognize whose face is a particular um, face, okay? So the goal of this session is to classify handwritten digits, and the left one is called binary classification and right one is called multi-class classification, right? So we are going to start with binary classification, and then once we are comfortable with binary classification, we'll just translate it into multi-class classification. All right. So now the MNIST data set is basically the full form of it is Modified National Institute of Standards and Technologies. They basically conducted they basically gathered the handwritten digits by high school students and employees of US Census Bureau. They asked, so they basically gathered these 70,000 small images, and then they they classified manually whether an image is one, two, or three or so. So they basically gathered this data from lots of high school students and the US Census Bureau, and and that way this data set is built. This data set is public and used globally, right? As of now, this data set, the neural networks have been able to achieve 99.7% accuracy on MNIST, okay? And that's the news you must have heard maybe 3-4 years back. And this is a great contribution by deep neural network. So whenever people come up with new data sets, people use MNIST. Also, we will try one more problem called Fashion MNIST in this session, because MNIST dataset is kind of showing its age. So there is another dataset. What they have done is exactly on the similar lines. What they did was they gathered the photos of lots of clothes, and you have to identify whether it's pant, shirt, or whether it's shorts, and so on, right? There are 10 kind of clothes you have to identify the way you are identifying the handwritten images here. All right, so let's get started. So that one we will add extra to this particular chapter, right? Now each image is labeled with the digit it represents, right? So this is an example of the MNIST dataset. MNIST dataset contains lots of rows, right? Each record is an image. Along with its label, that's a digit, that's a number saying that whether it's 1, 2, or up to 9. MNIST dataset is also called the hello world of machine learning. Whenever people come up with new algorithm, they test MNIST dataset to see how it performs. Now, in this dataset, each image is 28 by 28 pixel. 28 pixels is the height, and 28 pixel is the width. Okay, and which means if you multiply 28 by 28, it will give us 784 values. Okay, so if you arrange an image like this, right, like this, it'll have 784 pixels. All right, so each pixel is either on or off, and there are 70,000 such image. Actually, this is wrong. This line is wrong. The pixel is not either on or off. There is a pixel dense light. 255 means white, and 0 means absolutely black, and things are in between that. So what we have here is that there are 70,000 such images, which means 70,000 rows, and we can think of it like 784 pixels as columns. Now, the first thing we have to do is we have to Scikit-learn provides the modules called dataset, a module called datasets, in which there is this namespace called dataset, in which there is a module called fetch ML data, or you can say function called fetch ML data. So we imported that, and then we said mnist equals fetch ML data, right? Now, in this, you have to give this name mnist original. So it'll bring this particular dataset to you. It takes some time to download. It'll download it in your home drive in CloudX Lab home folder. Okay, so it'll basically create this mnist dataset. Mnist dataset is a dictionary that contains two keys. One is data, other is target. The data part we are putting it into X, and target we are putting it into Y, right? Now coming up, now here, so first of all, we are importing the datasets, right? And then if you take a look at this mnist, what is it? It's a dictionary, okay? Once it's downloaded, it doesn't re-download. So don't worry about calling this function again. All right, so here what we're doing is we are fetching the ML data, and this is our dictionary. This dictionary has these many keys. We have this description, and we have the column names, and we have the target, and we have the data, right? Okay, so if you see, where did it go? Here somewhere it basically keeps it there. Uh, Somewhere in your home drive, it keeps it. Okay. What does the notebook says? It says that, okay, fetch ML data downloads in the file structure called scikit-learn ML data, right? Oh, it doesn't? No. Let me try to search it a little bit more. Okay, let's see. So what find does is basically find lists all the files in that folder, and when we do grab, it basically grabs it. Okay, so oh, I think probably what it has done is it has created a folder called ML. Uh, That's the folder where we have kept. All right, now here inside the somewhere here. All right. So basically it has downloaded this in your home drive. Everybody's home drive is different, and that's where it has downloaded it. Okay, so how did it not appear? Yes. So if I delete this file, it'll re-download it. Okay. It's in a format called .mat. .mat format comes from MATLAB, and the data is in that format. So what it does is it basically first downloaded it and then loaded this file, loaded this data into this variable called mnist. Okay, it did both the things. So we are fetching it. It's not the data is generated already. We are just loading it. Okay. All right, I hope it is clear to everybody. Where is the data? Yes, it's a binary data. Take a look. So a quick way of taking a look at any file is using a command called file. File is the magic number. It checks what is that format. So it's essentially a MATLAB version 5 format. Okay, good. So moving ahead, and now let's take a look at the data and the target. Okay, so this is what we discussed. So now let's take a look at it. So we are assigning the yes, Arun, that's right. Fetch underscore ML data. The argument has to be exactly same because it searches it based on that name. Okay. So once you have done that, should we move ahead? Yes. A good question from Deepak is that once we have fetched the data and we are looking at this data, what we have is these keys, right? There is one key called description, DESCR, other is column names, then target and the data. Now, the target is an array of numbers, okay? And the data is again a matrix of numbers, okay? Now, what does data have? Data has 70,000 images, meaning the total number of rows in this is 70,000. And against every image, whether it has 1 or whether it has 9 or whether it has 0, that's marked. This one, this image that you see here is 0. This image that you see here is of 0. This image that you see here is of 0, right? While this image that you see here is of 9 and this image is of 9. So labels, target contains the labels, okay? While data contains the binary data of images. All right? So now let's pick the data part and the target part into two separate variables, okay? And take a look at the shape of X. Shape of X is 70,000 rows and 784 columns, right? These 784 columns, each column is representing one pixel frame from the image. It's a NumPy array, okay? It's a NumPy array. You can see ARREY, right? This means NumPy array. Okay. A question, yes, the target as index label. Now, target has basically the name of what character it is in the image. The data contains the images, and the target is the manually marked numbers for each image. Okay. So now this is supervised learning task. So we have got the data with the target. And so generally as a terminology, we put this way, the capital X is for the actual data and the small y is for target, okay? I'll talk about the conventions again. So let's understand the shape of X and Y. So X has 70,000 rows and 784 pixels. So how many features does X have? 784. Each pixel we are considering as a feature. We learn at later point of time that what are the other ways of representing image, the features of image, such as in case of convolution, we cut it into smaller tiles and that becomes our image. Now, coming back to it, so the now here the shape of Y is how much? 70,000 rows and one column. Okay, in basically it's a vector, therefore it's only a single dimension one, and therefore it's 70,000 values. Okay, one value per image. There are 70,000 images. right? Now, let's take a look at the data samples. First of all, we are importing matplot, right? And then we are just picking a image randomly. Here we have picked up 36,000. And so from the X, which contains around 70,000 image, we just picked up the middle one, approximately middle one, 36,001, and we are just reshaping it. We are reshaping this particular record. What will be the dimension of some digit? Some digit will be having having 784 values, and it'll be a single dimension array, right? It'll be a vector. So we are reshaping it into 2-dimension one. Okay. Again, you could miss this one and put -1 here. Okay. It'll automatically figure out that there got to be 28 rows. So we are converting our array of 784 values, right? This is an array of 784 values into 28 by 28 matrix, right? And then we're asking the PyPlot to show this image. So given list of numbers, it can show that image. It can basically plot it like this. All right, just take a look at what this particular image looks like. See, it's full of numbers, right? At 0000 and so on. And you can also see there's a pattern over here. Okay, let me just change a bit of. So this is our image. All right, doesn't look nice. Okay, so what I'm trying to see is if I could decrease the font size. All right, never mind. So basically, if you take a look at this pixel contains 86. 86 is the brightness of the pixel. If it is 255, that means it's entirely white, right? This is entirely white. I see. It looks like the other way. It's a negative image. So, all right. It's the other way. So 255, I think, represents the black, the dark side. Okay. And yeah. So this is essentially 255 means it's entirely black. 86 means it's slightly grayish somewhere here. This is a pixel, 86 probably. And 131 is probably the second pixel here. And then 255 is entirely black and so on, right? So if we subtract from 255, then it'll be better to represent it. Okay. So if I just, how do you subtract it from 255? 255 minus this, right? And I can also use the im.show. Let's see how it looks. Okay, so I'm going to subtract each of the pixels, right? Now you can see how easily we could convert a normal image into the negative of it, right? A question from Deepak is how we got 36,000. Basically, we just picked a random number. All right. You could also pick any other number. You could try picking 50,000. You could try picking any number between 0 and 70,000. All right. So this part we have done. This part we have done. All right. Now the steps that we are going to follow are these. Okay. Just like what we learned earlier, we're going to follow those steps. A question from Jay. X and Y coordinates should be from 0 to 25. X and Y coordinate should be from 0 to 25. Why should they be from 0 to 255. Is that, oh, here, it should be 28 by 28. This is 80. You know what has happened here is probably it subtracted everything. Okay, no, it's actually correct. So it's basically 28 by 28, and that's how. Yes, Arun, Deepak, Jay, Manoj, Nikita, Prashant, Robert, Robin, and Satyajit and Sumit. Okay, yes, yes. Also keep this open with you and also keep trying, keep experimenting there. Okay. Shape on what? The sum digit image. So it's basically 28 by 28. Why? We did the reshape here. Earlier before this, when we, if you take the shape of it, right, it'll look like this. Okay. The shape of this is 784 values. Okay. All right. So great, great. So far, I hope I would say that all of you should give it a try. Try exploring these data sets, know what is X and what is Y. We're going to use, as we go ahead, we're going to use capital X and small y. Okay, capital X stands for our data, the features, and the rows, right? And Y stands for the labels. All right. So the next step after loading the data set, the next step is we divide the data set into training and test. That's what we learned earlier. Okay. Divide the data set into training and into test. All right. So what we're going to do is we are going to split the data into training containing 60,000 out of 70,000 samples and test containing 10,000 out of 70,000 samples. All right. Usually you will follow the rigorous process of end-to-end project that we followed earlier. But here we're going to take a little bit shortcut in order to get to the results. All right. But ideally in your project, you should follow the standard process that we have followed in end-to-end project. Now we train the model on the training set and evaluate the performance of the model on the test set. That's what we're going to do. Okay. We're going to break this capital X into two parts, the test and train, right? The train one would contain 60,000 and test part will contain 10,000. Okay, so that's what we are going to do. The entire data set contains 70,000 images. Each image is nothing but 28 by 28 pixel, which is 784 pixels, right? And so we're just dividing the data set like this. Okay, that's not going to do much help, right? Um, this is here, right? We should be shuffling it first before dividing. Okay, okay, yeah. So we are taking first 60,000 record, putting it in X-train, then after that, we are taking the 60,000 records. After 60,000, we're putting it in test. Also, in case of Python, you can actually put commas and assign multiple values like this. So this gets assigned to the first one. This gets assigned to the second one. This gets assigned to the third one. And this gets assigned to the fourth one. Right? And then we are shuffling it. Okay. The one thing that is bothering me right now is this because these are ordered, right? So if we are picking up first 60,000, it's going to just pick first 60,000. So okay, I'll just show you what it means to me. So ytrain dot value counts, ytrain dot value counts. How will yeah, how will that happen? Did we import pandas? I'm not kind of convinced with this code here. I just want to see the distribution of the labels. Okay. Okay, so looks like the distribution is skewed, not much. Okay, not much. All right. Let me try this. So, okay, let me try this. So this is the value count in the. Okay, I'm just trying to see if my distribution is skewed. All right. So this is Y. Okay. All right. Looks like the distribution is not that skewed. Not bad. Okay. All right. So looks like the X and this capital X and Y is already sorted, right? And that's the reason. Okay. So I'm just trying to see the distribution between Y test, Y train, and Y, right? So you can see that it's not very much skewed. It's on the lines of the actual data. Okay. Since 4 is anyway lesser than, say, 1, similarly 4 is lesser than, a little bit lesser than 1. Okay. All right. Or we could just actually use the split. All right. So seems like this capital X and Y is already suffered. So we are taking first 60,000 into train, the next 60,000 into test. Same thing we are doing for the labels. You can see first 60,000 we are putting in the train, and next after 60,000 we are putting in the test, right? So there are 70,000, so we are putting 10,000 in the test and 60,000 in the train. Okay, Satyajit. So that's what we're doing. We're basically taking 60,000 and putting in the train and the test. All right. All right. I'll remove this part. Now everything back to where we were. Now after that, we are saying after that we are shuffling our data. And this is although there are inbuilt tools, but it's important to know that we could use this. So we can generate the permutation like this. Okay. We generate the permutation like this. What it will generate is, it'll generate a sequence of 60,000 numbers which are shuffled. Okay. So what we did was here, if you take a look at get yourself very comfortable with the notebook, right? If you say 5, it'll generate the uh, okay. So it will generate the permutation, any random permutation every time. Okay. And of course, here we are putting the seed so that every time the permutation is same, so results are predictable and we don't end up looking at the entire data set, right? So here what we're doing is we are, I mean, the reason here we are not applying the seed or random sampling. Instead, here we are just picking the first 60,000 records for training and next 10,000 record for testing. Now here, what you see is the getting the shuffle index, we can use a list of arrays as an argument to get the elements in that order, right? So So I hope this is clear to you what happens here. So first of all, we generated permutation, and then with the same shuffle index, we shuffled our X train, and with the same shuffle index, we shuffled the Y index, Y train. X train and Y train are now shuffled. Okay, make sense to you? No? Yes, moving ahead. Now, what we are going to do is we are going to use binary classification. What is binary classification? Binary or binomial classification is the task of classifying the elements of a given set into two groups, predicting which group each one belongs to on the basis of classification rule. Okay, so here we have the predicted positive class and predicted negative class. Okay, so binary classification is about yes and no, all right, meaning 0 and 1. So the label will basically contain true or false, okay, or 0 and 1. So it'll basically, instead of having multiple columns or multiple values, it'll have yes or no kind of thing in the label, right? Binary classification is the simplest to solve, and then we can use binary classification to do the multi-class. We will learn that part. Okay. So what we are going to do is we're going to figure out this classifier. We will figure out this classifier which can separate the values into positive or negative. Okay. This is like straight line perfect classifier. Now, here we are going to take an image and say whether it's 5 or not 5. For now, we're going to do this. Later on, when we move on to the full-fledged classification, we'll say that whether an image is 1 or not 1, 2 or not 2, 3 or not 2, and 3 or not 3, and so on. And that way, we could extend binary classification to multi-class, right? And then we're going to use stochastic gradient descent classifier for now. So we're going to talk about this in a little bit more details later, but for now, let's get started. All right. So if we just, if we had two things which have, let's say, only two dimensions, right? Two kinds of things, class 1, class 0. So what is it that we are trying to discuss here? We are trying to discuss what it means by classifier. Okay, so we are going to use this particular algorithm or this particular classifier in order to build the model, right? So if let's say we had two dimensions, two feature training sets, and we are trying to estimate the coefficient of the line. So let's say there are two data sets, this and this. We're trying to figure out this model which can separate the two classes, right? We're trying to figure out this model. So what we'll figure out is we'll figure out this line, which will be dividing the two categories. Okay, this will be dividing the two categories. So this is what we call a model, right? So we're going, this is the model, and anything which is above this is in class 1 and this is in class 0, right? So a classifier like here, the SGD classifier implements a plain stochastic gradient descent learning routine, supports different loss functions and penalties for classification, right? We're going to go more in details into this later. SGD classifier is capable of handling large data sets, deals with the training sets independently, and is well suited for online learning, right? We're going to use this particular one. We'll learn what it means by stochastic and how exactly it functions. But for now, this much is good enough to know that it is capable of handling large data sets and so on. Okay, so what's happening is here, if we had just two features, right? And we had to come up with, if we had just two features and we had to come up with a line that separate the two classes, right? What we'll do is we will come up, first of all, a criteria, kind of a formula, which tells us whether this line is doing good or not, right? So what we'll do, we will draw a line, a random line. Let's say we drew a line like this, okay? We drew a line like this somewhere, and then we calculate how many mistakes did we do. What we'll do is we'll go over the list of data points which are classified as one and are truly one, and we'll also go over the list of data points which are classified as zero and are truly zero, and vice versa. And then we'll count how much mistake our model has made, right? So what we're going to do is we're going to draw all possible. Classically, if we did not know any algorithm and we were just coming from computing background, so what we'll do is we'll basically we'll start drawing all possible lines. We'll start drawing all possible lines on this and figure out what is which line is separating this data point such that the line is also saying that this is the zeroth class and it is actually zero, and so on. So what is that best classifier? The brute force method or iterative method could have been that we draw all possible lines on this and figure out which one is making the minimum loss. Loss is what? The loss function, we call it. What it means by loss function is that represents loss function represents the overall loss. It's a formula that we have to come up usually, that means that it's a number that signifies how much mistake is our model making, right? We have to minimize that mistake. We have to minimize that mistake in almost every model. So first of all, we come up with a formula that that uh, converts all of this into a number, that what when we draw a line, what kind of error we are making. So quantifying that error is basically the loss function. Okay, so using loss function, we quantify the error that we are making at every point, and then we start drawing the lines. Now if we draw all possible lines, what will happen is we will end up with this infinite loop, which will take long time, and we will never get to a point, right? So what we do is we use something called gradient descent, right? Instead of trying all possible lines, we go into the direction that gives us better results. We go into the direction that gives us better results, right? So imagine yourself blindfolded on the mountainous terrain, right? And you have to find the lowest point. You have to find the lowest point. So what you do is you check under your feet. If you check under your feet, which side is going down, right? And you move that side. In case you are facing the other way, right? You turn around and move ahead, and then you again check what's under your feet and go in that. You keep on moving to the direction based on the slope. At every point of time, you're measuring the slope and you're moving ahead, right? So that's what we are going to do. We are going to measure the slope at every point wherever we land, and then see which direction is the slope of our slope, meaning which direction is slope, meaning the derivative derivative should be such that it should be taking us to the lowest point, right? So rate of change of the outcome should be in the direction where rate of change of slope here should be in the direction where we want to go. right? So that's what is happening here. This is a very simple example that we are blindfolded on mountainous terrain and we have to find the best lowest point, right? If so, what you do is you basically wherever you land, you check under your feet the slope, meaning you measure the rate of change. You basically subconsciously you are essentially doing the derivative, right? Okay, so you basically keep on doing that and you keep on in the direction, if in the direction of slope you move. Okay, that's what we do. So mathematically this is called gradient descent. Okay, a question from Manoj is sometimes there might be a temporary slope and then again a height. Is that a valid case? Yes, there could be the local minimas, meaning you got to end up in a very shallow pit, right? You did not realize that it is you are going down into the smaller pit and you end up there, right? So that kind of problem is solved by stochastic gradient descent. That's why we're using stochastic. What it does is every time it gives a random data point, it randomizes your approach, and and based on that, you move ahead. All right. So that's what we're going to do. Okay. So again, gradient descent, we will do detailed operations later. And gradient descent, once more, we will approach the gradient descent during neural networks. We will learn the newer techniques on gradient descent. Okay. A question from Robert is that part of learning rate? So learning rate, yes. So learning rate signifies how many steps are we taking before taking the next measurement. Okay. So okay, so this is how it will look like to you. Okay, so here is your loss function. If we draw the loss function, and here is the some, let's say some weight. All right, so what we're going to do is we are going to change the weight, reach to a point where the weight is minimum. So the way we do is instead of trying all possible weights, right, we could try infinitely all possible places, right? What we do is we basically at every point you compute the gradient, the rate of change, right? And we go in the direction where it's going down, just like we were doing in case of mountainous terrain. So we will basically, this is the initial position of W. So, and I mean here the weight signifies the model's weight inside the parameter, right? So what we're doing here is that we are here, we compute our gradient. Gradient is what? The rate of change of our loss. This is the loss function, right? And we are computing. Okay, so for now, right? First of all, we converted our problem into binary classification. What we did was we changed ytrain to ytrain underscore 5 by saying ytrain equals 5, right? Since the value, wherever it is 5, it'll become true. Wherever it's not 5, it'll become false. Okay. Now we initialized the stochastic gradient descent. Okay. We initialized stochastic gradient descent here, the classifier. For now, we can just assume that there is this wonderful classifier which will do the job. We will go into exactly how it functions. I've given you a very high level overview of what's going on in the gradient descent. We will do a detailed analysis of gradient descent soon. Okay, right? So here what we did was we initialized gradient descent classifier and we did fit, right? So we are training it with our X train and Y train underscore 5. Okay, so it is basically now trained. Okay, we'll skip this part. Okay, okay, so we have just trained our classifier. Okay, I'm going to skip this part. I'm going to skip this part. It's not required. Yeah. So here what we are doing is we are initializing the SGD classifier and then we are fitting it. So we have successfully trained our model. Okay, we've successfully trained our model. We're going to go more in detail into SGD classifier or gradient descent at later point of time, right? Once we have trained it, what we are doing is we are doing predict, right? So predict is just to test whether uh, whether it's working or not. So remember our 36,001. What was the number there? Right? Anybody? 5, right? Which means it is supposed to be true because we are testing whether 5 or not 5, right? So we are asking the SGD classifier to predict whether it's 5 or not 5, and it is saying true. So this is not bad, right? This is not bad. So we are, you can see that since the data was available up front, we were able to train it really quickly and get to the results. Okay, so the main part is not in calling the training method. The main part is in the peripheral works like preparing the data, cleaning the data, and so on. Remember our discussion on how to fill the missing values, how to average out the values, and so on. You should do the same thing in this also. You should scale these values. You should scale these values such that the values are between 0 and 1. You'll find that the performance gets improved if you do all those operations. I'll show you that part, that once we scale our images, you will see that our performance improves. Okay. A question from Manoj is that technically how it determined the that the given image is 5 matching the pixel pattern or some of the pixel values, or how. Okay, good question, good question, good question. So how many dimensions our data has? Our data has 784 dimensions. That's right. Each pixel is a dimension. So what it has done is it has drawn all possible planes under the hood, or it has basically drawn all possible planes that separate this data in 784 dimensions, right? If it has only one pixel, right? If let's say it has only one pixel, I'll just draw that. Imagine that it has only one pixel, right? If this pixel's value is say 255, it is true. If it's, let's say, 0, it's false. If it is 40, it's true, and so on, right? So if we have drawn this pixel on the x-axis, right, and these were the values, this is 250 first pixel, the okay, y-axis, it is true or false. So I'll just say 255, this is the, ouch. Okay, let me just draw it again. All right, so imagine that this is our first pixel, okay, and if this pixel's value is 0, this is like that. If the pixel's value is 255, it is like that. If the pixel is 40, it's again yes, right? So what it has done is it has basically plotted the pixel, each pixel in this way, and drawn a hyperplane such that this hyperplane separates yes and no clearly, okay, in all possible dimensions. Okay, So this is, let's say, pixel 1, and there is a pixel 2 similarly, right? And so on. So this is what it is doing. SGD classifier, what it did was it basically drew all possible such lines. It rotated it such that this line separates these pixels best in every possible dimensions. Okay, was I able to explain quickly? Should I explain again? All right, so imagine that there was only one pixel in the image, okay? And that pixel is, let's say, P1. And if its brightness is 255, then it's say yes, okay? Because this is our label. What is our label? Our label is whether it's 5 or not 5, right? So imagine that this is the scenario. We have, let's say, pixel 1, and the label is this. Similar, we will have like this 70,000 of such values, right? 70K such values, right? And what we'll do is what this under the hood, what it's going to do is going to take all the points, draw them draw them on this kind of plane, try to figure out that model that separates them really well, right? Now, it uses the gradient descent, meaning that it'll go in the direction which gives the better result. For example, let's say in the beginning, it's here. Let's say it drew the model like this. Now this is really bad. So what it'll do is it'll try to move it a little bit and then see if it's giving good results. If it's giving good results, then it'll just move it faster. Then if it's giving better results, we move it further faster. Okay. And since it's giving good results now, so it'll move it further faster and might land here. And then realize, oh, it's not separating very well. So it should start moving backwards. Okay. So that's how the gradient descent does. It is basically balancing this separator such that it is dividing the yes or no class properly. Yes, I'll say it. Arun, Deepak, Jay, Manoj, Nikita, Prashant, Robert, Robin, Satyajit, and Sumit. So it's doing it in 784 dimensions. We can't imagine 784 dimensions, but it is doing this in 784 dimensions. It's doing it for all the pixels. A question from Manoj is, so it's comparing with the pattern of other 5 labeled images. That's right. If not other 70,000, 60,000 actually, because 60,000 is what is in the training, right? So it draws the line, finds how many pixels are to the yes side or no side. So it's going to do 60,000 comparisons on every time it draws a single line, right? So, and this is it's doing it in all possible planes. Okay. So it is comparing with the patterns of other 5 labeled images, or say it's comparing both, right? So this is 5 and not 5, right? So it drew a model. This model is supposed to mark this side as yes and this side as no. Okay. And but let's say or let me this side as no and this side is yes, right? And it realized that, okay, there are, right, it's making that kind of mistake. Okay, so what it'll do is it'll basically move this line such that all the things on this side are no and all the things this side are yes. And of course, it's not going to happen that all the things are yes, or all the things are no, or all the things are yes. It's going to be some kind of a loss, some kind of a number, and that number is what it wants to minimize, right? The overall loss. A question from Manoj is why we took 60,000 for training. Should it not be vice versa? No, it should be, we should have training data as 80%, testing data as 20%, right? All right. Prashant, Robert, Robin, Satyajit, Sumit, Al Sayed, Arun, Deepak, Jay, Manoj, Nikita. Is this idea clear? So all it did was took one pixel, right, and drew whether it's yes or no, right? It knows that each pixel is yes or no, and then it started drawing this line such that the, let's say on this side of it is yes, it's this side is no, right? And it'll basically try to draw that, balance it out, and when it reaches here it'll kind of settle down, right? Because it'll try going up, it'll see, oh, there's a lot, they go back, then it'll say, okay, I'm making no mistake, and then it'll keep on going this way. Just like a pendulum, it'll try to come to that balancing point, right? And it's going to do the same thing in this dimension as well, and we'll keep on doing that, right? Now, the exact strategy of this we are going to discuss very soon. But before that, let's try to be a little bit more practical and do a little bit more hands-on, right? So how does it, how to test the performance of it, right? We checked, okay, it's doing good on one particular image, right? It's doing good on one particular image, this particular classifier. We want to know that how good it's doing on rest of the images, okay? We want to know that how it's doing on rest of the images, okay? So, okay, so, all right. So basically the one particular image is okay, but what we do, how do we figure out it's doing good or not, okay? We've just checked once, we can't really go on checking each ones and just pick like 3 samples randomly and be happy that it has predicted well. That's not the way we should measure the performance. We should measure the performance in a right way, and this is very, very important. And the reason we have the classification chapter as second is mainly for this part, okay? The everything before it is mechanical in the sense that we just run the commands. We really don't know how exactly the stochastic gradient descent works, but for but here the purpose was this, okay? So the performance matrix is something that we would like to know on what basis we say that this model is great and this model is bad and so on, right? So the performance matrix is basically many kinds. There is something called cross-validation accuracy, then confusion matrix, and so on, right? So what is cross-validation? Now, what we're going to do is, we have already learned what is cross-validation. It involves splitting the training set into k distinct subsets called folds. We train and evaluate the model k times, picking k different folds for the evaluation every time, and training on the other k minus 1 folds. So first of all, we break our data set into k folds, right? Or we mark our data set into k folds. We run our training k times, picking each of the folds as the testing data for evaluation, and remaining k minus 1 folds for the training. So we train k times, we test k times, and figure out how well we are doing. And at every time when we are doing cross-validation, we will be using some performance measure, right? The result is an array containing k evaluation score. There can be different evaluation methods like accuracy, average precision, etc. So this is what we mean by cross-validation. So cross-val score, as discussed in end-to-end project, Cross-val score function in scikit-learn can be used to perform cross-validation just like this. So what we can do is we can run the same SGD classifier instead of running like this, running SGD classifier.fit. We let cross-val score function run SGD underscore CLF.fit on those K folds. Okay, so on those in those K, I mean using the cross-validation strategy. So that's what it does. Okay, so let's go down here. So we are running the same model. Remember this, we did exactly same thing in case of end-to-end project, whereby we gave cross-validation, cross-val score our model and let it train in these many iterations. So it's using these many iterations, 10 iterations here. The training and test data has been provided to it. And here, notice that scoring function. Right now, we are just using a method called accuracy, right? And you can see that the accuracy here seems to be like this, okay? Now let's understand, okay? See, the resulting accuracy here, if let's say the folds were 3, the resulting accuracy is 95, 96, close to 97, and 96. So the resulting accuracy is above 95% for each of the folds. Okay. So do you think the resulting accuracy is 95%? Of 95% is good enough? The answer is that the accuracy may not be a good performance measure when we are dealing with a skewed data set. Ours is a skewed data set with only 10% of the data as the digits 5, right? What is the worst case scenario? So let me put it this other way. Do you think 95% accuracy is good enough? We are talking about 5 and not 5 kind of labels, right? Okay, let's take a detailed example. Imagine that we had really dumb classifier. You see, we designed this, we thought we were pretty smart, so we designed this new classifier called never 5. Now all it does is every time it is called to predict, in case of training it's not doing anything, it's not learning anything, but in case of prediction all it does is it returns no, it returns false for everything. Whatever image you give, it'll say that it's not right, right? All of these images are not 5. For every image that you are asking it to predict, it's returning zeros. Okay, how many zeros? Zeros equal to the number of rows in X. Okay, so this never 5 classifier returns blindly false for everything. What will be the accuracy of this one? Anybody? It blindly replies that it's not 5. How many 5s are there in the data set? 10%, right? And how many are not 5? 90%, right? So how many times this never 5 classifier return zeros? 100% times, right? Because every time it's returning 0, meaning saying, hey, it's not 5. So how many times will it be right? How many times it'll be right? Because it's saying it's not 5. It's not 5. For everything, it's not 5, right? For 1, it's saying not 5. 2, it's saying not 5. For 3, it's saying not 5. For 4, it's saying not 5. And for 5, it's saying not 5. For 6, it's saying not 5. For 7, it's saying not 5. How many times it's right? What is the accuracy? Anybody? So the never 5 classifier is going to say no to everything, right? No to 1, no to 2, no to 3, no to 4, no to 5, and so on. That is not 5. Okay. So what will be the the accuracy of never 5 classifier. So yes, the answer is you're right. It is going to be 90%. All right. If anybody is not clear, I can clarify it. Why it's 90%? Because it's only wrong in the case where uh, there is 5, correct? Because it's saying all the time that it's not 5. So when truly something is 5, it's saying no there. That means it's only wrong in the case where the it's actually 5, correct? And how many numbers are those? Those are 10% numbers, because this data set is well balanced. This data set is well balanced. So 10% of one, 10% of two, and so on. So this never 5 classifier is wrong only in the cases where there are fives, correct? And which is 10% cases. And hence the accuracy here is 90%, right? So never classifier is giving us 90% accuracy, and our SGD classifier is giving us 95% accuracy, right? So are you happy with that? The answer is it's not good enough. It probably is not good enough, but we need to figure it out, because even a dumb classifier is giving an accuracy of 90%. We need a better measure of performance for the classifier. We need a better measure. Okay, so how do we come up with those measurements? So let's talk about the performance metrics. How do we analyze whether a model is doing good or not, right? So the first way is to prepare the confusion matrix. What is a confusion matrix? So if there is a data imbalance in your data set, you might end up believing that your algorithm is doing good, but it may not do good, right? So you need to come up with a better measure of performance. Okay, you cannot have all the time all the classes to have the same accurate same frequency or same occurrences. Okay, so that's why we need to have a better measure of performance. Okay, better measure, and that's what we're going to do. All right, so a general idea is to count the number of times the instance of class A are classified as class B. Okay, so it can be better than simple accuracy. So what we do is we create this confusion matrix. Okay, we create this confusion matrix. We write down this kind of matrix. We say these are 4 blocks, right? True, positive. This is actual. If the actual matches the prediction, we call it the true positive. Okay, so this is true and this is false. So true positive, and this is false negative. Okay, and this is okay. So what we do is we write this in boxes that how many of them are actually positive but have been classified as positive. Similarly, we write down in this box how many of the instances were actually 5 but classified as not 5. Okay, then here in this box what we write is how many of those were negative and classified as positive, meaning how many of them were not 5 but classified as 5. Similarly here, we say that how many of them were actually not 5 and classified as not 5, meaning these two boxes represent the correct things and these two boxes represent the wrong thing, right? So ideally, in the best case scenario, these two should be 0. These two should be the maximum possible, right? Two should be equal to the actual numbers. Is it clear what it means by confusion matrix? So confusion matrix essentially, in case of binary classes, it's 2 by 2 matrix. If there are 10 classes, then it'll be 10 by 10 matrix. Okay, if we are classifying things into A, B, C, D, and up to Z, then it'll be 26 by 26 matrix, right? All right. In our case, let's take a look. Let's take a look in our case. The here actually these many were not 5 and classified as not 5, meaning this prediction is correct. These many were 5 and classified as 5, meaning these are the ones that are correct. Now these are the wrong ones, as in 1300, there were 1300 such instances where actually the image was of not 5, but our model predicted as 5. In 1000 cases, 1077 cases, the model actually, the image actually was of 5, but it was classified or predicted as not 5. Okay, so this is called confusion matrix. This is true negative, this is false positive, this is true positive, this is false negative. Okay, so the ones that are with starting with true, that those are basically the correct values. Starting with false are the ones that are wrongly classified. Okay, so true positive, true negative, we need to maximize those, whilst false positive and false negative is we need to minimize those. Is everybody clear about it? What will be the total of all? If we had, let's say, 60,000 total images, what will be the total of all these four numbers? That's right, it'll be 60,000. I'll say it, Arun, Deepak, Jay, Manoj, Nikita, Prashant, Robert, Robin, Satyajit, Sumit. Is this confusion matrix clear? So we had 60,000 instances. We fed those 60,000 instances to our predictor. We noticed the outcome, and then we drew this matrix saying what was actually 5 and predicted as 5, what was actually 5 and predicted as 5, what was actually not 5 and predicted as not 5. Okay, this is called confusion matrix. All right, so using confusion matrix, multiple kind of measures are created, and using those we measure the performance of our model. Okay, it's pretty simple. All you need to do is you need to do here, not there. Okay, just before we move ahead, so never 5 classify, let's take its performance. It's actually 91%. You can see approximately 91%. Now let's use a method called cross val predict. Okay, and these are the predictions. Okay, so these are the predictions, right? We can create confusion matrix in a very simple fashion. All we need to do is we need to just import confusion matrix. We need to just import confusion matrix, call it on actual versus predicted. Okay, call it on actual versus predicted. And here we have, so this is true positive, sorry, false negative. This is true positive. Sorry, this is true negative, and this is true positive. This is true negative, and this is true positive, because only these many are 5 and these many are not 5. This is false negative and this is false positive. Okay, so here you can read. All right, now so all we used a function called cross confusion matrix, and it gave us the results. All right, everybody's clear about confusion matrix. Moving ahead, now there is something called precision and recall. Okay, before we jump ahead, so this is true negative, meaning there was no 5 and it was predicted as not 5. This is true positive. Okay, these are true positive, and and meaning they were 5 and were predicted as 5. Now this is false positive. They were not 5 but predicted as 5. Right? These are false negative. They are 5 but predicted as not 5. Okay. Now, okay. So now let's understand the other terminology called precision and recall. Question from Sumit is, any reason why the model did not pick up those and got into issues? Yes, we are going to go into the detail that what's wrong with this and what's wrong with this, right? Of course, you can see that they look a little confusing to us. And similarly here, we'll also understand how to improve those by looking at the data. Okay. A question from Manoj is that a couple of generic questions. All these libraries have function named fit and they work in same fashion. Is that correct? Yes, that's right. All in scikit-learn, our general philosophy is that almost every class that seems like a predictor, they have two methods. One is fit and predict. As well as every class has got a constructor. What is a constructor? The constructor is something that is used for initializing or creating an object, and we can pass attributes to it. Okay. So all these library. Okay. So I hope that clears. A question is, all these libraries take the data in same input? Yes, good point, very good point. So all these libraries in scikit-learn, they take the data in the form of NumPy, okay? NumPy array. The data from another problem will be in a different format. That's right, but what we have to do is we have to translate the data from other formats into a NumPy array, okay? That's something you got to do. Remember our discussion that where we converted the category classes into one hot encoding and so on, right? So if our data is not in the number format, we have to convert it into numeric format. So great, great. Now we learned two things. We first learned that accuracy may be misleading, right? And it could be misleading, and so we learned about confusion matrix. Now from confusion matrix, we can we can compute the precision. Now we have to precisely learn the definition of precision and recall and similar term, because this is a common question people do ask very often, that what do we mean by precision? Okay, precision is true positive divided by true positive plus false positive, meaning the things in first row. Okay, things in first column, I think. True positive and false positive. True positive and false positive, right? True positive and false positive, meaning how many were, so this is called precision. How many were 5 divided by how many were correctly predicted as 5 divided by how many were predicted as 5. Okay, so no, actually, this is false positive. This is, yeah. How many of them were predicted as 5? Okay, so some of the values here got predicted as 5. Some of the values which were actually 5 were predicted as 5. So, so the way we compute precision is this value divided by total of this column. So, okay. So if this value is 0, meaning there is no 5 that got, there is no other number, there's no other number that got predicted as 5, right? If this value is 0, if this value is 0, which means that if any other number did not get predicted as 0, then the precision will be 1, meaning only and only 5 gets predicted as 5. Okay, then the precision will be 1, right? So how many 5 were predicted as correctly divided by how many 5 were predicted as correctly plus how many other numbers were predicted as 5. So this amounts to the precision. This amounts to the precision. I hope it's clear. We are not dividing by total numbers here. We are only dividing by the predicted 5s. Okay, predicted positives. True positive divided by predicted positives. Okay, so irrespective of what was the distribution, here we're talking about the precision or the behavior of the predictor. Okay, so here we are saying that how many were truly predicted as 5 divided by how many total were predicted as 5. Okay, so precision is clear to all. Now the recall rate. Okay, how many of the total classes we were able to recall? That's the recall rate, irrespective of how many mistakes did we make. Okay, so here we are saying that true positive divided by true positive plus false negative. Okay, false negative. What is false negative? False negative is this part, meaning that it was the 5 got predicted as not 5. Okay, so everything here. Okay, so meaning how many were total 5 in the input, how many were total 5 in the input, and how many of those were correctly predicted. Okay, how many were the total 5 in the input and how many of it was able to recall, right? That's what is the recall rate. While the precision is how many were truly predicted as 5 divided by, meaning out of all the 5s that were predicted, out of all the 5s that were predicted, how many were actually 5. Okay, so that's the precision, and this is the recall. Recall means in the recall, when we say we want to improve the recall, the chances are that we will hurt the accuracy. Okay, out of total 5, how many of it got predicted as 5, right? When we increase the recall, what happens is we will end up predicted something else as well. We will end up something as 5. Let's say there is a classifier that you wrote. Let's say there's a classifier that you wrote, and that classifiers, what it does is it always returns 5. Always it returns 5 for everything. What will it do is here for everything it'll return 5. Okay, so in all the cases, all the positive cases, it will be 5. And here also, all the values will be 5, predicted as positive, right? So what will happen in case there is a classifier whose name is, whose job is to predict everything as 5, what will be the precision? Anybody? For everything, it's saying it's 5. That's right. It will be 1 by, you can say 1, you can say basically it'll be 10%. Thank you, Nikita. So the precision is going to be 10. And what will be the recall in such case if there is a classifier which always gives 5? It says for everything it's 5. What will be the recall rate? For everything it is saying 5, meaning there is nothing in the first column here. Okay, so the recall rate for such a classifier is going to be 100%. So the precision is say 10% and the recall rate is 100%. All right, because this is 0. All right, so while the recall rate is 100%, or you can say 1, the precision is around 0.1. Okay, is everybody clear about the recall and precision? Okay, let's take a look at the precision score. There's a method called precision score and recall score, which you can always use, or you can compute your own. All right, so we go down here. Okay, so you can see the precision score is 0.8 and recall score is 0.7, right? That's not bad. All right, so where is that never 5 predictions? All right, never 5 classifier. I'll just use this. Okay, we'll see. Okay, predict x underscore train, right? All right, so we're going to try this out and see what happens. All right. All right, so looks like the never 5 case, the recall rate is anyway 0. The precision rate is also 0 because true positive is 0, right? Because true positive is 0, correct? What happens in the case where we define something called always 5 classifier? Okay, let's try that out. Okay, so I mean the reason why I'm doing this is to make all of you know more handy with it. Okay, always 5 classifier. All right, so let's see. Okay, right. Okay, what's wrong with it? Anybody? So I just defined something called always 5 classifier, right? And using always 5 classifier, I am trying to predict the, okay, here I have not changed it. Now you can see that. The recall rate of always 5 classifier is 1, while the precision score is approximately 10%. It's actually 9%, right? I hope that is clear to all. Great. Now, so as we saw that while the recall rate went to 1, the precision dropped down to 0, right? Dropped down to really low, like 9%. Okay. I'll just delete this. All right. Great. Great. So that was precision and recall, and we also learned about the confusion matrix. Now let's learn about a very interesting concept called F1 score, right? Now, what happens usually is that when we increase the precision, recall goes down, and when we increase the recall, the precision goes down, right? Always 5 had like perfect recall, but the precision was really low. So you can see that the model on the either extreme, right, could be misleading, though precision seems to be a better way of measuring the model's quality. But again, a number of times what happens is that when we increase the precision, the recall goes down, and when the recall goes up, precision goes down. And therefore uh, we are always in a kind of scenario, either we want precision or recall, but in reality we want both. If we want both, then we use F1 score. F1 score is basically this. It's called harmonic sum. Okay, I think it's called harmonic mean, not sum. Harmonic mean. Okay, it's essentially the way you look at it. It's essentially F1 score is essentially like this. Okay, 2 by F1 equals 1 by recall plus 1 by precision. Okay, 1 by precision. Okay, this is recall. Okay, so what did I write? Okay, so this is like that. And when you put these values like this, it becomes something of this like formula. And when we put it in terms of true positive and true and false negative, we get this, right? So true positive divided by true positive plus the average of false negative as well as false positives. Okay, that's the F1 score. So idea is to maximize the true positive by bringing down both the false negative as close to 0 as possible. Okay, so the purpose is to bring up the false negatives and bring down the sum of false negatives and false positives as close to 0 as possible. Okay. All right, moving ahead. So I hope the F1 score is clear to all. So The way we compute the F1 score is again by importing F1 underscores score from the matrix and calling it on the actual value versus predicted value. Okay, so this is how we compute it. So all we do is we import F1 score, right? We import F1 score and we calculate the F1 score by providing the actual versus predicted, right? All right. So a question from Deepak is F1 score enough? 70%. It looks good. It looks good. But when we compare multiple models, we will see that the F1 score of 70% is not really very good. There are better models which could do better than this. Okay. Now, what's more important is that understanding when to use precision, when to use recall, and when to use F1 score. And Deepak's question is that earlier we achieved 95%. That was not F1 score. That was the accuracy, right? That accuracy could be misleading for our kind of problem statement. Okay. All right. Now, a question always remains that what to use, whether to use precision, whether to use recall, or should we use F1 score? So it depends on the use case. Simple answer is that based on your use case, you would require precision or recall, right? Imagine that you are trying to detect videos that are unsafe for kids, right? Let's say you are trying to detect videos that are unsafe for kids. What would you want? You would want precision to be high. Maybe the recall rate is low. Okay, meaning the false positive should be low and false negative can be high, right? So meaning something that is unsafe should not go as safe, while if there is some video which is safe, let it be categorized as unsafe. So precision should be really high at the cost of recall rate, correct? Correct. So the precision, in case of, let's say we are trying to figure out which videos are great for kids or which videos are safe for kids, in that case, we would want the precisions to be really high. Okay, we would want precision to be really high. Now, on the other hand, let's say we are trying to detect shoplifters in the surveillance. The recall rate, we would want it to be high so that let the person who is not a shoplifter be marked as the somebody who is a shoplifter and let they be checked. Okay, let their basket be checked and let they be frisked. Okay, so the case here is that in case the ones that we have you know, the people who are not shoplifters, if we mark them as shoplifters, it's not going to do any damage here. We are just going to check them. That's all. Why? While here we cannot afford to mark a wrong video, an unsafe video as safe, right? Therefore, in this case, we require the precision. In this case, we require the recall rate to be high. Okay? That's right. So point from Manoj is, so when we don't want to leave anything behind, then we need high recall rate. Yes. Okay, when we don't want to. We are okay with something wrongly classified as the main class, while the true class. And but we don't want to leave anything behind. We are okay with wrongly classifying. In case of precision, we are not okay with wrongly classifying. Okay, we may let go of many predictions. Okay, so that's the idea about precision and recall. A question from Sumit is how having an F1 score can improve the accuracy. It doesn't. So accuracy is a different measure. F1 score is a different measure. And why we choose the precision, recall, and F1 score is because accuracy was misleading. As we proved using an example of Never 5, whereby Never 5's accuracy was 90%, while it's actually a dumb classifier, right? So having F1 score, precision, and recall gives you far more finer control over what is it that you are expecting. If you're based on the problem statement, you would like to choose precision or recall or F1 score, right? Question from Sumit is there any way to increase accuracy? Yes, there are ways to increase accuracy. We'll use a more complex model. We'll use more ways, but it's important to first describe what it means by accuracy to you. Okay, accuracy statistically means all the things that are correct divided by all the things that are wrong. Uh, uh, out of total predictions, what are the correct predictions? That's accuracy, right? Correct predictions divided by total number of instances, right? And we proved that that was not great. So we need to come up with the measurement, the performance measure that we want in our problem statement. Okay. So there are ways to improve accuracy, precision, and recall. But before moving in there, we should know what it means by accuracy, what it means by performance to you. All right. And these definitions of precision, recall, and F1 score and accuracy, they help you understand what is it that we are looking for. All right. Question is, in real time, what will be the expectation? Again, first of all, when we are talking about a problem like a machine learning problem of classification, you should always grill or ask yourself or the people who are involved in the project that what is the meaning of great prediction? Does it mean precision? Does it mean recall? Does it mean accuracy? Or does it mean both precision as well as recall? That is F1 score. Okay, so before you start the project, that's the question you need to ask. Okay, and once you know that this is what it means by the performance to me, then we improve our models, we improve our entire way of doing machine learning in order to improve this performance metrics. Okay, did I understand your question, Sumit, correctly? All right, I hope I was able to answer. Okay, so theoretically, in case of the STD classifier, we were drawing a line, right? That was basically our decision function. So the classification is done on the basis of a score calculated by the decision function in STD classifier. Yes. So a point from Sumit is that the ML is a continuous process till we get desired result. ML is a continuous process. This is the digit recognition or prediction example that we are talking right now. This example has been there since 1980s, and people have been continuously improving its performance. Okay. Similarly, in organizations, the models keep improving all the time, and so on. So it's a continuous process. There is a continuous process of getting desired result every time. Okay, so that's how it is. So every time we get desired result, then it gets improved, then we get better results and so on. Okay. Question from Deepak is, so product managers of projects should be clear about ML terminologies concept. That's correct, Deepak. And that's one of the reasons why we started a AI for Managers course in which we teach these precision and recall trade-offs. Because what we were realizing when we were, some of our learners who were interacting with product managers or who were themselves product managers, they were struggling all the time with the terminologies, and they had no clue, while they kept on insisting on things like accuracy. And when somebody said precision, they thought that precision and accuracy is all the same thing, and that's why we started that. Very, yeah, that's very good point, Deepak. So a product owner should know what they want. Correct, correct. The product owner, because the truth is that we may think that we know what we want, but to express it, we need this kind of terms, these kind of words like precision, recall, F1 score, right? Otherwise, it becomes extremely vague and we can't communicate. Question from Manoj is, to predict digits of stricken of captchas, we will need a sample data if stricken of digits and current data will not work. That's correct. That's correct. But again, you could give it a shot, and I want to see how it works. Okay, give it a shot. Okay. The other thing is that mostly the captchas have multiple characters, so we'll have to figure out how to detect the character in an image and then see if we can use the classification. Okay. How do you recognize characters in an image? You basically move a window and see which window is fitting, which window is being predicted as a image. Okay. A question from Deepak is, okay, nothing much. Question from Sumit is, what challenges you face while doing a project, as it is never ending process? All right. So as long as the outcome of your project is better than human, you deploy it. Okay. Whatever is your default current process, if the predictions are better than that, you deploy it. Okay. And you can continuously keep on improving as more and more models, better models, or things keep coming, and so on, right? The challenge basically, okay, so what challenges you face while doing a project? There are humongous number of challenges when we are doing a project in case of machine learning, and I'll go through the challenges once more when we go towards the end of the course. All right. So great, great. So classification is done on the basis of some kind of score that is calculated by the decision function of your model, right? If the score is above certain threshold, is classified as positive class. If the score is below certain threshold, is classified as negative class. So I was talking about this case, right? Yeah. I was talking about this case that we are trying to draw this line such that on one side everything is negative class, on the other side everything is positive class. Now the what we are saying is, this is, let's say this is the model, this is the threshold. When we want to predict something, we'll basically ask this guy that, hey, is this a negative or positive class? Then he'll say that you exist on this side of my line, therefore you will be the negative class. If somebody comes here, right, pixel value is this much, right? So it'll say that, okay, you are some other value, okay? So this way, there is certain kind of some kind of threshold that is figured out by the classifier, and if as the as the score changes, the negative and positive predictions ratio keep on changing. For example, here you can see that here, how many fives are there on the right hand side? All right. Therefore, the recall rate is 100%. Is that right? The recall rate 1, 2, 3, 4, 5, 6, 6 out of 6, right? Well, precision is how much? 1, 2, 3, 4, 5, 6, 7, 8. So out of total 6 that are predicted correctly, 8 are the total predictions. Okay, so only 6 out of 8 predictions are accurate. Therefore, the precision is 75%. Correct? Is everybody clear about this? So most of the classifier have something called a score internally, and if the score is above certain threshold, a class is classified as negative or positive. So if you change the threshold, the total number of negative classes and positive classes will change, right? So as our threshold is here, our recall rate is this much, right? Okay, is this correct? So recall rate here is 100% and precision is 75. Is everybody clear about this? No? So let's say there is some kind of a score internally. When that score is low, everything is, a number of other characters are being predicted as 5. So 2 is predicted as 5, 6 is predicted as 5, while these are not predicted as 5. This gives us a recall rate of 100% and precision. Now we'll fine tune our algorithm and realize that if we increase our score to somewhere here, what happens is some of the 5s are not being predicted correctly because they are being predicted as not 5. Therefore, what is the accuracy? The accuracy is 1, 2, 3, 4, 4 by how many? 4 by 6. Okay, so that's your recall rate. And what is the precision? Precision is total number of fives that are predicted, 1, 2, 3, 4, 4 by 5. Correct? There are total number of 5, 6. Total number of values that are predicted is 5. Okay, that are classified as positive, but out of which there were only 4 classes which were positive class. So you can see that as the recall rate is rising, because we are decreasing threshold. So as the recall rate is rising, the precision is, sorry, as the recall rate is dropping down, the precision is rising. Okay. What about this one? If our boundary, the decision boundary is here, meaning 3 out of 3 which are predicted are 5, and out of total 6, we have only predicted 3 as 5, right? Only 3 numbers as 5. So what is the precision and recall at this point? Precision is 100% as per Deepak, and recall is 50%. Okay, anybody else? Right? I'll say Ed, Arun, Deepak, Jay, Manoj, Nikita, Prashant, Robert, Robin, Satyajit, Sumit. Could you respond? So what is the recall and precision if our decision boundary is here? Decision boundary is a boundary based on which something is predicted or not predicted. Okay. As per this decision boundary, these many are predicted as 5, while it has let go of these 3 5s. Yes, so that's right. That's right. 3 by 3, that's precision. All the things that are predicted as 5 are really 5. And also all the things that are predicted, all of them are 5. Okay. Recall rate is 3 out of 6. So there were total 6 5 digits, and we were able to predict only 3. Okay. Therefore, it is 50%. All right. So increasing precision reduces recall rate, and vice versa. Raising the threshold, increasing the precision, and decreases. If you increase the threshold, increase threshold means if we shift the decision boundary. Okay. So if we are increasing the threshold to the right, it's increasing in precision and decreasing the recall rate. If you drop down the threshold, everything will be classified as 5. Okay. So what we do is we fine tune the threshold in order to get the desired recall and precision trade-off. Okay. So for a threshold of 0, classifier will correctly classify 5 as 5, everything. Okay. For threshold of 20,000, the 20,000 just number for the threshold. Okay. And classify incorrectly classifies digit 5 or not 5. So if the threshold is really high, then everything will be classified as 5. Okay. Sorry. So if the threshold is really high, only few digits. No, this. So if the threshold is really low, it will incorrectly classify everything as 5. While threshold is very high, it will kind of even the most of the 5 digits will be incorrectly classified as not 5. Okay, so most of the models give you the decision function that you can find out. So you can always compute the decision function by using a function called decision underscore function, and you can pass a digit and it'll tell you what has been the decision function for this prediction. Okay, a question from Manoj is, can you iterate on accuracy versus precision. So precision is clear to all. The accuracy is nothing but total correct predictions divided by total numbers. Okay, that's accuracy. Whatever is the total input record size, that's your in the denominator. In case of accuracy, numerator is true positive plus true negative. True positive plus true negative divided by total numbers. All right. All right, let's take a look. So this decision function is this, right? We could check the decision functions against the scores and do the prediction. Okay, and so on, right? So hence, by selecting the appropriate threshold, the user can obtain the desired precision. However, the best precision may not have the best recall, right? So get the scores, how to decide the best threshold. Threshold of the decision function, that we are shifting that line from left to right, right? So that we can adjust precision and recall. Well, how to do that? How to decide upon the threshold? We get the scores of all the training sets, data set using cross-val predict with decision function as a function, and compute the precision and recall for all possible threshold using precision recall curve. Okay, plot both decision and recall for the threshold using matplotlib. Select the threshold value that gives the best precision recall trade-off to the task at hand. Okay, so the idea is that using the cross-val predict, there is a function called cross-val predict. Using that, you predict the decision function. Okay, this basically will give you all the thresholds, and then you draw the precision recall curve. Okay, using the method called precision recall curve, it'll give you the precisions, recalls, and threshold when you pass this. Okay, now how to plot the this precision recall versus threshold? Okay, so the way you do is that first of all, precision recalls and threshold you pass as argument, and then you plot each of them. I'll just show you this. What does it say? It says that precisions, recalls, and threshold equals precision recall curve, precision recall, and this. Okay, let's see what happens if I put it here. Oh, looks like we chose. So Y scores, how much are those? Let's just check. There's something. Okay, this looks, I see. So Y scores are these. And why is it so that, all right, this is how it looks like. So we have defined a function called plot precision recall threshold, to which we'll be passing the precision, recalls, and thresholds. That's okay. Now, somewhere there is a method called precision recall curve, to which if we give Y train and Y score, it gives the results. So okay. Okay, so precision recall curve, Y train and Y score. Not really. I see. Just a second, I'll just put. Okay, so precision recall curve, we pass the Y truths, then probability predictions. Okay. Okay, so this is what we do. Precision recall curve, Y true and Y scores. So what are the Y scores here? These are the Y scores. And if I, so we have this, okay? And what do we want? We want basically probably these scores that you see on this side. Cross-val predict. What does cross-val predict? Basically give us this decision function. Ideally, we should be having this here. The okay, there is something either wrong or scikit-learn I changed. So what's happening here is that what we are trying to do is we are trying to get the threshold from all, and once we get the threshold, we'll be plotting the recall versus the recall versus the we'll be computing recall, the precision, and the threshold. Okay, those are the three things that we are going to do. And okay, now it looks like this is dead. I'll have to restart it. All right, let me just restart the kernel. All right, so good. I'm just trying to see how can we plot this part. I'll run everything above. So run all above. It might take a bit of time. In the meantime, we could just take a look at the precision recall curve. Okay. So it says that precision recall curve computes the precision recall pairs for different probability thresholds. Okay. Now the right precision is this, recall is this, the right, and once it is done with that, it basically gives you the threshold, the precision, and the recall. So here, the other method that we have is this, correct? Cross-val predict, right? You could put cross-val predict, put a question mark. Cross-val predict has an estimator that we are giving, that we are passing here. The second one is your X-train data. Then we are passing the Y, right? Y train, and we are explicitly saying that the CV is equals to 3, right? So it generates the cross-validated estimates for each data point. It is not appropriate to pass these predictions into cross-validate to measure the generalized error. That's okay. And here that when you see the method, what is the method here? Method is a string. By default is predict. Okay. So what if we do predict prob A? All right. Now what we got is we got here the Y scores, correct? Now the Y scores look all okay. So we are saying give me all the rows, but give me only the column, right? So that correct, right? So 314371247, yeah. So we'll say give me all the rows and give me only the first column. This is my Y scores, right? And can I use this one? Okay. No. Yes, looks like this time it worked. Okay, so that's a bit of difference. All right, so let's try to plot it. Perfect, right? So what we did was we calculated the thresholds here. We calculated the thresholds using the decision function. It gave us list of all the thresholds for this for these X train and Y train. Instead of doing the prediction, it did that. And once we recovered that, we extracted only first column. Okay, we extracted only first column, and that was the main issue with this code. Probably it's using the previous API. And then what we did was we plotted it. So you can clearly see here that as the precision is increasing, right, the recall is going down, right? Or you can say that as the threshold increases, you can see as the threshold is increasing, the recall goes down and the precision goes up. Okay. All right, so that's pretty much for today. We will continue from here. We'll continue from the ROC, these curves, the precision, recall, and threshold curve. And yes, so all you need to do is probably just change this to this. Okay, that should work. You just add one more line after this, and that should work. All right. So that's pretty much. And I'll be committing this piece of code. Should I commit it? Okay, I'll just delete this, delete this, delete this, and delete this. Okay. So we'll continue from the precision and recall further. We'll learn about ROC curve. We will learn how it works, and then we will start with the science behind the machine learning. So far, we have been looking at things from application perspective, how to get things done using the program, and how to evaluate the outcome. That's what we have learned. And so that's pretty much for today. I'm going to commit the code, and if you have any questions, you can ask.